How did over 1 billion years of rock go missing? The Grand Canyon contains one of the most complete geological records on Earth. Its layers are an open book laying out the sordid history of our planet. But not the whole history. There are millions of years missing, even over 1 billion in some locations. That's quite a lot of missing pages. So where did they go? Hello, I'm Sage, and this is Crash Course Geology.
Ah, the Grand Canyon. It's big, it's grand, it's canyon-y. The indigenous Paiute described it as a mountain lying down, and 19th century geologist John Wesley Powell called it a library of the gods. And for good reason. The stripes on the canyon walls are storytellers called strata, layers of rock that record what the planet was like in the deep past. These are the three main chunks of the strata in the Grand Canyon: the Vishnu basement rocks, the Grand Canyon supergroup, and the layered Paleozoic rocks. A beautiful array of igneous, metamorphic, and sedimentary. Looking good, old GC. Strata can tell us about all sorts of geologic activity. Floods, tectonic movements, changes in sea level, volcanic eruptions, and even more. And because strata are well preserved and exposed in the Grand Canyon, geologists can read those rocks to uncover the story of our planet, including the mystery of why some chapters are missing.
The layers know something, but they're just not talking! Or maybe I just gotta speak their language.
If strata are chapters in Earth's biography, then sediment is the alphabet. Worn down fragments of rock that get moved and deposited somewhere else. That's where the story really begins. I mean, we can't read anything without the ABCs. Through sedimentology, geologists study how rocks transform into sediment, and sediment transforms into rocks, which goes a little something like this. Weathering wears down rocks, creating sediment. Erosion by water, wind, ice, or gravity physically removes that sediment and puts it somewhere else. Often, it's deposited in basins, areas of land that sit at slightly lower elevations than the surrounding landscape, like the massive Colorado River Basin, home to the Grand Canyon. When conditions are right, sediment can get buried so deep that it turns into solid sedimentary rock. Layers of rock pile up as beds, layered beds become strata, and voila, another juicy chapter in Earth's tell-all memoir. Dwayne and I are in a book club. Oh, and by the way, if you're also really into rocks, you should check out the SciShow Rocks Box, a cool rock delivered straight to your door every month. I mean, what could be better than that? Check out the link below to learn more. Except Earth is constantly editing and rewriting the record. In a lot of places, erosion washes away the evidence, or the strata are simply buried too deep to observe. But not in the Grand Canyon. Here, the rocks are both very old and very well preserved. We can use it to look back 270 million years ago, at a minimum. But most of the canyon itself was carved only in the past 5 to 6 million years by erosion from the Colorado River. It's kind of a brain teaser. The Grand Canyon itself is much, much younger than even the youngest rocks it's made of. Only in geology can something that happened 5 million years ago qualify as recent history. Also, sedimentary rocks hold clues to what a place was like at the time the sediment was deposited. Ripples, mud cracks, and angled layers called crossbeds can tell us which way the wind was blowing or water was flowing, how intensely it was doing so, and if there was a dry spell after sediment was deposited. But beyond a snapshot in time, rocks can also tell a bigger story over millions, even billions of years. Stratigraphy, or the study of the geological record through strata, is how geologists understand the relationships between layers of rock and the events from the deep past. Come on, Dwayne, we're going to the bottom of this baby. No, I didn't rent a mule. You know that I think their teeth are freaky. But yes, I will carry you. At the top of the canyon's top layer are sedimentary strata that show periods when the landscape was at the bottom of a shallow sea. Sediment deposited during those watery times contain fossils of marine organisms that died here. But we can also tell that there were times when sea levels dropped and the water retreated, because those sedimentary layers have no marine fossils. Deeper down and further back in the past, we can find evidence of early single-celled life in that middle section of the rock, called the Grand Canyon supergroup. Free band name. At the very bottom of the canyon, the metamorphic and igneous Vishnu basement layer, better free band name, tells us what Earth's crust was like over 1.3 billion years ago, as volcanic island chains smashed into what was then the edge of our continent. But stratigraphy doesn't just tell us what happened in Earth's history. It can also help us figure out when things happened, through relative dating. Relative dating uses relationships between strata to determine whether an event in the rock record happened before or after other events. This technique can't put a number on how old rocks are. That's what absolute dating methods are for, which we'll get into in the next episode. But it can help us put a timeline together. Oh, what's that, Dwayne? Your dating app keeps recommending 500-million-year-old rocks even though you put your age limit at 200 million? I think we're thinking of different kinds of dating, bud. Geologists have a few guiding principles for figuring out how old a layer of rock is. One of them is the principle of faunal succession. They use fossils of a species that were only alive during a specific time period to infer the age of the rocks they're found in. Like, trilobites were on Earth for a limited time, and different types of these creepy crawlies had brief moments to shine. So when the same type of trilobites are found in rock layers in two different places, we can assume they're around the same age. Also, we can assume that higher up rock layers formed after the rocks below them. That follows the principle of superposition. Rocks below other rocks are older than the layers above. It's kind of like making sand art. You can tell I added the orange sand first because it's at the bottom, and the green sand last because it's at the top. And each layer of sand in between is added in the exact chronological layer I poured them. Then there's the principle of original horizontality. Sediment beds are deposited in flat-ish lines pulled by gravity. So if sedimentary rock layers don't rest roughly horizontally, we can assume something, like shifting tectonic plates, knock them into a wonky shape after sediment solidified into stone. The same goes for layers of igneous rock. Sometimes, one layer of rock just barges into another at an angle. According to the principle of cross-cutting relation, rock layers doing the interrupting must be younger than the rock being interrupted. Classic younger sibling energy. Let's take a look at some of these principles at play at the Grand Canyon. We can assume the Vishnu basement rocks are older than any of the rocks above them, based on the principle of superposition. And the chunk of igneous rock must be younger than the metamorphic rock it intruded into, because of the principle of cross-cutting relation. Above the basement rocks, the Grand Canyon supergroup tilts at an angle. From the principle of original horizontality, we can assume geologic forces shoved those rocks out of position. And above that, the layers lie horizontally, so we know they haven't been disturbed since they first formed. All that covers a massive time span. The rocks at the bottom are roughly 1.75 billion years old, and the ones at the top, around 270 million. That's older than the oldest dinosaurs. But I know what you're thinking. Sage, when are we going to talk about the billions of years of missing rock? Now is the time, my friends. The Grand Canyon's rock record is astonishing, but it actually covers less geologic time than the giant chunks that are missing. The gaps in the timeline are called unconformities, boundaries between two sections of rock that represent a gap in the geological record. The results look a bit different depending on the rocks that were around at the time. And these different types of unconformities have different names. Like our first example, a nonconformity. I know it's annoyingly similar to unconformity, just go with me. A nonconformity is a surface where erosion wears down a layer of igneous or metamorphic rock before new sediments are eventually deposited on top. You can see that here. The rocks at the bottom of the Grand Canyon's metamorphic basement that formed about 1.75 billion years ago. But the top of these rocks were eroded. So the timeline doesn't pick up again until just over 1 billion years later, when the layers of sedimentary rock begin. You can also get a disconformity, where erosion wears down the top horizontal layers of sedimentary rock. Then more sediment washes in, stacking other horizontal layers on top. And if the older rocks were tilted at an angle before they're eroded, you've got yourself an angular unconformity. The most famous gap in the Grand Canyon's timeline happens along these two spots, where the layered Paleozoic rock meets the Vishnu basement rocks, or, in some places, touch the Grand Canyon supergroup. It's called the Great Unconformity. I don't know what to tell you. Geologists don't take a class on how to name stuff. In some spots, the Great Unconformity skips about 250 million years of the geological record. And in others, as much as 1.2 billion years of history are just missing. That's about 25% of the Earth's biography, either erased or never recorded. And while the Grand Canyon might be the easiest place to see it, this gap exists in rock layers everywhere. It's just usually hidden. So what did Earth do? Take a gap year that turned into a cool 1 billion years? Well, there's a couple theories. One possibility is that powerful glaciers eroded the landscape during a period when Earth's surface was totally frozen. Another theory proposes that when a past supercontinent called Rodinia began to break apart, the land shot upward and erosion wiped away a billion years of evidence. Kind of like a giant Etch-a-Sketch. And still others theorize that what looks like one global event actually took place over multiple periods of massive erosion or little sediment deposition. It's a mystery geologists haven't quite solved yet.
You've evaded me this time, great unconformity. But one day I'll catch you.
The Grand Canyon's stunning layers might be a familiar sight in a road trip photo album, but there's so much more than that. They're the best record we've got of what happened in our planet's distant past. Let me tell you, it's a real page-turner. Even when some chapters are missing, reading rocks helps us understand Earth's many phases and changes, shaped by forces that still act on the planet today. Rocks have stories to tell us, and stories they're keeping to themselves. At least for now. Next time, we're headed back in geologic time. We'll see you then. Thanks for watching this episode of Crash Course Geology, which was filmed at our studio in Indianapolis, Indiana, and was made with the help of all these nice people. If you want to help keep Crash Course free, for everyone, forever, you can join our community on Patreon.